real quantum world, but you can take this scenario, push the scenario, and then compare what happens with noise, without of noise, and with that get a better understanding of your actual quantum device. Mm-hmm. Yes?
When using true quantum, how are you handling the error rates?
When I use quantum? Yeah. So ultimately, we know what to do. You need to implement quantum error correction. That's the holy grail in the community. But we've seen a lot of progress, I would say, over the last few years, with several labs and companies reporting on the first logical qubits. So what that means is you take several error-prone physical qubits, you smash them together, and what you get is one perfect error-free qubit, and that is what we call the logical qubit. It's errors also happen in classical computers. Yeah, so you can
a lot faster here, though.
Yeah, that is true. Yeah, that's why it's such a challenge. But we don't know any fundamental limitation. It's a hard challenge, for sure. But there's no fundamental limitation to realizing quantum error correction. Yes?
So in your different platforms that you guys offer
Yep.
to people want to use your machines, but in your testing, have you found that certain platforms perform better for certain types of problems, or are they all equal? So
That's a good question. So there's not a short answer to this, because I think it really depends on your application. Some applications may require all-to-all connectivity. Then your best guess would be trapped ions. They offer all-to-all connectivity. In other applications, you need maybe fast turnaround times because your time budget is small and finite. Then your go-to platform might be superconducting qubits, simply because their clock rates are just order of magnitudes faster than trapped ions, for example. As of today, I don't think there is one size fits all. It really depends on the application and the requirements for this application. And that's why I think it makes a lot of sense to have these different portfolios all sitting next to each other, and then it takes you change one line of code, and then you can run your same quantum circuit against trapped ions or superconducting qubits, and then you can evaluate what works better for you. Yep.
What kind of applications are you developing when it comes to combining quantum computing with AI or machine learning so far?
Well, this is an emerging gigantic research area. Broadly speaking, I would categorize into two subcategories. There is AI for quantum and quantum for AI. AI for quantum is important these days, and that's something that we look into, is in quantum error correction. So you get these errors, you measure syndromes, and now the question is, how do you correct them? And people are looking into AI neural networks to do this efficiently, because this has to happen fast. You don't want this to be the bottleneck in your calculation. The other way is, I think, more future-looking. This is quantum for AI. We know that quantum computing has algorithms that will provide a speed up, for example, for matrix multiplication. Today's transformers, they do a whole bunch of matrix multiplication. So there's a potential one example of where you could aim for quantum speedups in machine learning.
Yeah, I'm saying, maybe I didn't catch you. What aspects do the speeds happen most likely?
Sorry, can you say it again?
So, what aspects of machine learning would quantum computing most likely speed up?
But it's generic, right? So you do a lot of matrix multiplication.
Oh, yeah.
Yeah, every matrix multiplication you could speed up. Yeah.
I see.
Yeah. Could be a transformer, could be any kind of network that you want. I mean, a lot of it is, at the end of the day, deep learning is all about matrix multiplication. Yeah. Yeah.
You touched on your partnerships with pharma to support clinical trials.
Yes.
Could you elaborate? Was that more patient selection, site selection?
Site selection. Yeah. Site selection. Right. So you can frame it as an optimization problem. Happy to talk about this in detail. Yeah. Okay. Any more questions? No? Okay. Thank you.
Thank you.